Hi, so Shardy. It's a new open source MLIR-based propagation and partitioning system that we've been developing over the last year within Google and Google DeepMind. But first, I want to go over some background information for those unfamiliar with scaling large tensor programs. Like the generative AI models like Gemini, ChatGPT, and others that generate text, images, audio, and video are extremely large. And due to how big and how many matrix multiplications there are inside them, these companies have to deploy the models across thousands of devices. But how does this deployment work if the model can't even fit on a single device? So for a bit more context, we need to understand how the accelerators are set up. There's some differences between Google's TPUs and NVIDIA's GPUs, but simply put, they have various different fast inter-chip connections that lets these accelerators communicate with each other. However, that's just how the physical systems are set up. Like when researchers distribute their models across the chips, they operate on what we call a logical mesh that abstracts away the details of the underlying hardware topology. You, of course, need to account for the various connection speeds that can exist in large systems, since not all connection speeds are the exact same. Two common distribution, or from now what we call sharding strategies, is batch and tensor parallelism. Batch parallelism has you split up your samples across multiple chips to calculate the predictions in parallel, while tensor parallelism has you split the parameter tensors of your model across devices and compute partial activations before communicating them together. For example, if we were doing batch parallelism, then each row of devices gets a unique slice of samples. And for tensor parallelism, each column gets a unique slice of the parameter tensor. You can think of each row as having the entire model just split across the 3 devices, and each column computing its subset of activations across all of the samples. Let's quickly see how a program is written on the 4x2 mesh for tensor parallelism. We're going to look at a super small program where we just do 2 matrix multiplications, and here I'm going to just show the very final program after propagation and partitioning each device will see. So we're going to use a strategy which lets us calculate the 2 matmul's in parallel before we're forced to take the summation across all hosts due to the contracted dimension on that second matmul here, the %1 being sharded. To do so, we need to shard dimensions of size 64 in param1 and param2, you see highlighted here. Now, after propagation partitioning, you can see that all reduce being added due to the contracting dimension of the second matmul being sharded. So this is kind of pretty neat, but we have systems which do this all for us, so we don't need to modify every single operation in the graph and add collectors ourselves. So let's take a look at some of them. Note I'm only going to focus on the sharding propagation part, not the partitioning or that SPMD-ifier part, the thing that adds the all reduces here. So just the propagation part. So first we have GSPMD, which is the first in these sets of systems. It is an attribute-based propagation system which doesn't have access names and propagates ops in a predefined order. It also has a pretty extensive sharding conflict resolution strategy built into it. We then have PartIR, which instead of propagating sharding attributes, rewrites the program into what we call tiling loops. It also uses named axes on the mesh, has a data structure that tells the system how an arbitrary op can be sharded, but doesn't have a conflict resolution strategy. Since it asks users to define sharding strategies as separate propagation passes. And then finally, we have the mesh dialect, which is upstream into MLIR. It uses a combination of ops and attributes for propagation. It doesn't use axis names, only axis sizes on their mesh, and has users implement an interface to tell the system how to propagate through an op. And then finally, we're introducing Shardy, which borrows a lot of ideas from GSPMD and PartIR. We use a mesh with axis names we propagate shardings like GSPMD. We use a mesh with axis names like PartIR. We have both op-based and user or round-based propagation like GSPMD and PartIR. And finally, we also have an interface for telling us how to shard like the mesh dialect, but looks more closely to what PartIR has with its data structure than the mesh dialect. And we'll get to what it looks like exactly soon.
Yeah, let me introduce the new sharding representation, and we also define a set of sharding APIs for the ease of user annotations. As an overview, the sharding is an attribute of an operation, which describes how the results of the operations are partitioned. It's usually bound to a mesh. In this example, this sharding is bound to this mesh, and the first dimension is partitioned along W first, and then along X. The second dimension doesn't shard it along any axis, which means this dimension is fully replicated, and the axis Y and Z are not used in this sharding, which means they are implicitly replicated in this for this tensor. Also, we define the source and target of the sharding propagation. First of all, we define the explicitly replicated axis, which cannot be used to further partition the tensors. And on the contrary, the in-place replicate axis can be further used to partition tensors, which are the axes to be propagated in the propagation stage. For the target part, on the target side, we define the if dimension is open or closed. The open dimensions can be further sharded using the axis, while the closed dimensions cannot be further sharded. And the source can only be the in-place replicate axis, and the target can only be the open dimensions. We also provide the priorities for the users. These priorities can be used to determine the propagation order, which providing the more user control and the better debuggability for the users. For example, it's easier for users to implement a different level of hierarchy of propagation with different priorities. For example, it's easier to implement batch parallelism at the highest priority, and then with the magnetron sharding followed by the zero shardings. And this priority can be attached to the sharding annotations as shown on the right example. We just attached P0 to the specific sharding annotations, which demonstrate this sharding has the highest priority to be propagated. Also, we define the sharding rules, which visualize and simplifies the propagation algorithm. This sharding rule demonstrates the relationship between the dimensions across different tensors. For example, as taking a dot as an example, its sharding rules is just its annotation in ISOM in essence. We can define using this annotation to define the batch dimensions, non-contract dimensions, and the contract dimensions easily. And it's easier to visualize as shown in the next section how we demonstrate how we propagate the shardings along the factors. And this sharding rules just provides a visualization of this sharding relationship. And we propagate shardings with three directions. The first one is the forward directions, which is propagating from the operands to the results. Also, we support the backward propagation and sideways propagation, which is between different operands and between different results. Next section, we discuss how we propagate shardings in this with this sharding annotations and the new APIs. This graph is an overview of how we propagate shardings. It's in essence, we propagate the shardings along the factors. To do that, we have three key steps. The first one is the projection from the dimension sharding to the factor sharding, and we propagate the shardings along the factors, and then we project back to the dimension sharding space. And as we discussed, as we mentioned in the slides before, the dimension sharding and factor sharding, their relationship is bounded by this sharding rule. Let's take an example with the dot. In this dot general, it's just very standard, very simplified version. It has two non-contract dimensions and one contract dimensions. And the first step to handle this propagation is we project the shardings from the dimension space to the factor space. And to do that, we have this sharding rules, which is equivalent to the ISOM notation. It's just IK, KJ, and we project the result. It just corresponds to two non-contracted dimensions. And for each factors, we also have the size, which corresponds to the original dimension size. With these sharding rules, we can project the shardings from the dimension space to the factor space, which in this example is quite simple. That we have three factors, and since we only have the sharding axis in LHS, we can just fill this table with the corresponding cells. Note that several tensors doesn't contain all the factors. For example, the LHS doesn't contain the RHS non-contract dimensions, which means factor J is missing in the LHS. Now we proceed with the second step, is propagate shardings along these factors. First of all, we can just propagate shardings along the factor I. Since there is no conflict, we will just propagate the sharding axis batch directly along this column. Similarly, we can propagate tensor axis along the column, along the factor K. Yeah. The third step, we project vector shardings back to the dimension space to form the original tensor sharding. And since the relationship between the vector sharding and dimension sharding is formed by these sharding rules, we can directly project back to the dimension space. In this example, the RHS will get the tensor along the factor k, and the result will get the batch axis along the factor I. Yeah, the example above doesn't contain any conflict resolution requirements, since there is no conflicts in these tables. We do not have the repeating axis along each column or repeating axis along each row. So when we further develop a full hierarchy to resolve these conflicts, on the top level, which is the user priority propagation, users can define the priorities for specific sharding annotations, and we will handle this highest priority, handle the sharding with highest priority at first, and then gradually handle the shardings with lower priorities. With that priority, users can easily implement the batch parallelism and maximum zero sharding annotation hierarchy. And in the second layer is the operation priority propagation, which is a heuristic method borrowed from JSMD. We will handle specific pass-through operations at first, and then gradually handle several complicated operations. For example, we will always propagate the element-wise operation at first and handle this dot. Dot will have a lower priority than the element-wise operations. And third level is we develop a kinds of different different strategies to resolve the conflicts in a single priority. For example, when we have the conflicts across different factors, or we have conflicts along a single column, we cannot propagate the batch axis along a single column easily. We can discuss more details after in the QA or offline. And the bottom layer is the basic propagation, which is apply the specific strategy and propagate shardings in this along factors in the factor sharding space. We also would like to emphasize that all these passes are following the same interface, and we extend the basic propagation to the highest level, such that all these propagation strategies following the same interface, and they are just the outer layer just is the derived classes of the base layers of the bottom layers.
Yes, now we'll talk a little bit about wanting to be Shardy to be dialect agnostic, and kind of our long-term goal is to kind of make Shardy a kind of standalone component able to work with any MLIR dialect. At the moment, we directly depend on stable HLO, but we are making progress towards lifting that through various abstractions and interfaces I'll get through here. The first one are sharding rules, and as Sean already discussed, this attribute encodes how we can propagate through a specific operation, and as long as an operation implements this interface, Shardy will be able to propagate through it. The next one are region-based ops. So these companies like while loops, case op, etc. And they're more complicated that we need to make sure we can propagate into and out of them. And kind of our sharding rules aren't enough for this, since they only describe the correspondence between operands and results, but region ops don't have such a relationship. So we've defined a shardable data flow op interface, where we define various methods to tell us what value on the operand plus block arg barrier and region terminator plus op result barrier owns the shardings. And I'll skip the details of this for offline discussions of the various methods and how they're used, but overall the point is we have a way to handle any arbitrary region-based op. And then we have constant splitting. So like most tensor programs in MLIR that we see, we have one instance of the constant that is reused by whatever op that needs that value. This makes sense when the constant needed is the same. However, when sharding a program, we want each use to have the constant it specifically needs and not be affected by how other ops use that constant. And kind of what I mean is we want to allow each use of a constant to have a different sharded constant if they request one. Like just because two parts of a program are using some constant value shouldn't mean they're sharded the same. For example, on the right, if the add is sharded, why should the divide and subtract in different parts of the computation also be sharded the same way as the constants? It really doesn't make sense. When we call this a false dependency, since like every constants are cheap and there is a real dependency of ops that use that same constants. As such, we ask users to tell us what is their constant op, and also what ops are constant-like, such as iota, and what ops are foldable. To recall, GSVMD has the style of op-based propagation where they propagate element-wise ops first, and then ops like mapmul. And this needs to be configurable by end users since we don't know about their dialects, we don't know about their ops. And as such, we just need the user to specify them for us. So we'll ask them to pass a list of ops in the order they want Shardy to propagate them in. Yeah, and that's like everything that's needed to make Shardy propagation work. More work would be needed for the SBMification or the partitioning BAS. I think that's the collectives. But that's our focus next year. And now debugging. So what we want to focus on as the main benefit of Shardy over other systems is improved debuggability and interpretability. We've just about finished working on the core propagation algorithm. So we've started looking at creating debugging tools for users to understand what propagation did. And here we will describe just one of them that we've been working on. So for some background, there's a tool called Model Explorer that was open sourced by Google back in May. And lets you visualize different graph types, including MLIR, and does so extremely fast. And like some of you may have already seen this talk during the MLIR workshop this past Tuesday. And yeah, since propagation deals with these giant graphs, we want to use it to help understand where their shardings come from. As to recall, the end user annotates their graph with a few sharding attributes on their function inputs, their outputs, and some intermediates, and Shardy propagates them all around the graph. So for example, here, shows like an MLIR graph after propagation. And looking at that multiply op, can we really determine where axis A and B kind of come from? Not really. So what we like to do is store extra information during the MLIR reroute pattern that does propagation and save metadata on top of the graph, lets us visualize the trace of where each axis came from. So here we see axis A through the jot general, then the add, and finally input 0. And axis B came from the graph output. And the way we do so is using the MLIR action tracing framework. We create an action when we're about to update the shardings of an ops operand's results, which figures out the op local trace information. And then we have a handler which saves this for the entire program. And then after propagation is done, we'll save these for Model Explorer to understand.
Yeah, the final section we discussed about how we experience Shardy today. At this stage, Shardy now depends on the stable HO. So the users can specify a stable HO module as an input with the partial sharding annotations. Users can specify the partial annotations using the APIs we discussed above, or using the specific APIs to demonstrate how users would like to partition several ops. And we will apply the Shardy propagation pipeline to propagate shardings to the whole graph. You can either use the SDLPT or use the C++ path on the modules with partial sharding annotations. Finally, the result will be the module with the shardings all over the graph. For example, now you can experience Shardy directly in the JAX. In the JAX, you can just enable this flag using the Shardy partitioner, and with original JAX sharding-related APIs. For example, the JAX name sharding, JAX mesh, JAX sharding constraint, and so on. And we will just lower it to Shardy representation directly. For example, we lower the name sharding to the Shardy sharding. We lower the JAX mesh to the Shardy mesh. We lower the JAX sharding constraint to the Shardy sharding constraint directly, and we can just apply the propagation pipeline directly on the module with partial shardings. Further, we'll just apply the partitioner. Partition provided by the XOA and other XOA passes to obtain the machine code on different hardware backends. Yeah, here are several future directions we'd like to explore. First of all, we'd like to implement and devise this partitioner in the Shardy using the original Shardy dialect, and which will be our major focus next year. We would like to extend our support to other ML frameworks, especially for the PyTorch. Currently, Shardy depends on using the Bazel to build the whole system, and CMake will be the support for the CMake is on the way. Finally, we would like to make the Shardy fully dialect agnostic and make it detached to the current stable HO. Yeah.
Yeah, so that's Shardy. Yeah, we hope you've now gained some new insights into how engineers are using compilers to scale their kind of AI models across 1,000 devices, and a bit more about some fun tools in MLR like action tracing and model explorer. And finally, we hope you give Shardy a try. Thank you.